And in the traditional architecture of liquid rocket engines, the injector plate is often the site of a violent, chaotic struggle against time and physics. To understand the profound leap represented by the Raptor 3 full-flow staged combustion cycle, one must first visualize the phase barrier that hampers almost every other engine in history. And in a standard engine, such as the Merlin or the RS-25 Space Shuttle main engine, propellants arrive at the injector head as cryogenic liquids dense, cold, and stubborn. To release their chemical energy, these liquids must undergo a series of rapid physical transformations. They must be atomized into fine droplets, heated to their boiling point, evaporated into a vapor, and finally mixed with the opposing reactant at a molecular level. Only after this sequence of physical pre-processing can the actual chemical reaction, the combustion, begin. And imagine trying to start a massive, high-intensity fire by spraying a garden hose of liquid gasoline into a room. The liquid doesn't burn instantly. It streaks through the air, pools in corners, and creates a localized environment that is too rich in some spots and too lean in others. This is the latency of evaporation. In a rocket engine, this latency is a liability. It forces engineers to build larger, heavier combustion chambers to give the liquid droplets enough residence time to fully evaporate and burn before they are swept out of the nozzle. If a droplet exits the nozzle before it finishes burning, its energy is lost to the vacuum of space, a thermodynamic cash miss that degrades the engine's efficiency. And the Raptor 3 bypasses this entire bottleneck through its full-flow architecture. By the time the methane and oxygen reach the main chamber, the liquids are gone. They have been processed by the pre-burners into high-energy, high-pressure gases. This is the gas-to-gas advantage. The engine is no longer trying to mix a liquid stream with a gaseous cloud. Instead, it is colliding two screaming tornadoes of gas. And the physics of molecular interpenetration. When two liquids meet, they form an interface, a physical boundary that must be broken down through mechanical shearing and heat transfer. This is a relatively slow process. However, when two gases meet, they interpenetrate at the molecular level almost instantaneously. This is driven by the kinetic theory of gases. The molecules are already in a high-energy state, moving at incredible velocities, and they require no additional energy to break out of a liquid phase. And in the Raptor 3 combustion chamber, the mixing length, the physical distance required for the fuel and oxidizer to become a homogeneous mixture, is drastically reduced. This allows for a much more compact combustion chamber design. From a structural standpoint, a smaller chamber is a lighter chamber, and it is also a chamber that is easier to cool. By shrinking the volume where the most intense heat release occurs, SpaceX can concentrate the energy of the propellants with surgical precision. And for the computer science professional, this can be viewed as the difference between just-in-time compilation and AOT, or ahead-of-time compilation. In a liquid injection engine, the hardware has to perform the compilation, specifically evaporation and mixing, during the execution loop, which is combustion. This adds latency and increases the risk of execution errors like combustion instability. In the Raptor 3, the propellants are precompiled into a gaseous state by the pre-burners. By the time they reach the main chamber, the data, or the chemical potential, is already in a format that the processor, or the combustion zone, can execute with zero overhead. And symmetrical power, the full-flow mandate. The full-flow designation is not merely a marketing term. It describes a fundamental shift in mass flow symmetry. In previous staged combustion engines, like the Russian RD-180 or the American RS-25, only a portion of the propellant flow was used to drive the turbopumps. And in the RS-25, for example, a small amount of liquid oxygen was mixed with a large amount of hydrogen in the pre-burners to create a fuel-rich gas. While this gas was then sent to the main chamber, a significant portion of the liquid oxygen bypassed the turbines and was injected directly into the chamber as a cold liquid. This created a phase mismatch. You had hot, gaseous hydrogen trying to mix with cold, liquid oxygen. The resulting combustion was efficient, but it was also incredibly stressful on the hardware due to the extreme temperature gradients across the injector plate. And the Raptor 3 achieves a state of thermodynamic symmetry. In this system, 100% of the liquid oxygen passes through the oxygen turbopump and its associated pre-burner, and 100% of the liquid methane passes through the methane turbopump and its pre-burner. There are no bypass lines for the main flow. And this creates a balanced system, where both sides of the injector are dealing with gaseous streams of similar energy densities. This symmetry simplifies the manifold design and ensures that the pressure distribution across the injector face is uniform. In the high-stakes environment of a 300-bar combustion chamber, uniformity is the primary defense against hot spots, localized areas of extreme temperature that can melt through an injector or a chamber wall in milliseconds. And taming the beast, stability at extreme pressures, one of the greatest ghosts in the machine for rocket engineers, is combustion instability. This occurs when the pressure fluctuations in the combustion chamber synchronize with the frequency of the propellant injection, creating a resonance loop. If left unchecked, these chugging or screeching frequencies can act like a jackhammer, vibrating the engine until it undergoes a structural failure. And historically, liquid-to-liquid or liquid-to-gas injection systems are highly susceptible to these instabilities because the evaporation lag acts as a variable delay in the system's feedback loop. If the pressure in the chamber spikes, it can momentarily slow down the evaporation of the incoming liquid droplets, which then causes a pressure drop, which then accelerates the evaporation, leading to another spike. This is a classic unstable oscillation in a control system. And the Raptor's gas-to-gas mixing effectively short-circuits this feedback loop. Because there is no phase change, no liquid-to-gas transition occurring in the main chamber, the primary source of that variable delay is eliminated. The gas is ready to react the moment it enters. This high-bandwidth response allows the Raptor 3 to operate at chamber pressures that would destroy other engines. And at 300 to 350 bar, the Raptor is operating in a regime where the propellants are often supercritical a state, where the distinction between liquid and gas begins to blur. However, by ensuring they are fully gaseous and high temperature before they meet, SpaceX has created a laminar-like combustion environment even at turbulent, supersonic flows. It is the difference between a crowd of people trying to push through a single-door, liquid injection, and a synchronized military parade moving in formation, gas-to-gas injection. And the serialization of propellant flow to further refine the mental model of FFSC, we can look at it through the lens of data serialization. In a complex software architecture, if you have multiple threads trying to write to the same memory address simultaneously without a clear protocol, you get race conditions and data corruption. And in a rocket engine, the memory is the combustion chamber, and the threads are the propellant streams. A liquid injection engine has low-fidelity threads. The droplets are of different sizes, they evaporate at different rates, and they arrive at the combustion zone at slightly different times. This is unserialized data. And the Raptor 3 serializes its propellant streams by passing the entirety of the fuel and oxidizer through their respective pre-burners. It ensures that every molecule of methane is in the same gaseous state, and every molecule of oxygen is in the same gaseous state. When these two serialized streams meet at the injector, the reaction is predictable, repeatable, and incredibly fast. And this serialization is what allows the Raptor to achieve its record-breaking specific impulse in such a compact form factor. The engine is essentially pre-processing the chaos of the propellant into a high-order stream of energy. And the mechanical dividend of full flow. Beyond the combustion efficiency, the full flow architecture provides a critical mechanical advantage. It allows the turbines to run cooler while still delivering more power. And in a non-full flow engine, you have to squeeze a lot of power out of a small amount of working fluid, the gas used to spin the turbine. This requires the gas to be extremely hot, which pushes the turbine blades to their thermal limits. In the Raptor's full flow cycle, because all of the propellant is going through the turbines, you have a much larger mass of working fluid available. And think of it like trying to turn a heavy water wheel. You can either hit it with a tiny, high-pressure jet of steam, known as staged combustion, or you can hit it with the entire flow of a massive river, which is full flow. Because the Raptor has the entire river of methane and oxygen at its disposal, it can achieve the necessary torque to drive the high-pressure pumps at lower turbine temperatures than would otherwise be possible. And this is the great paradox of the Raptor number 3. It is the most powerful and high-pressure engine in the world. Yet by using the full flow cycle, it actually reduces the thermal stress on its most sensitive internal components, the turbine blades relative to the work they are performing. This mechanical dividend is the secret to the engine's potential for rapid reusability. By spreading the work of driving the pumps across the entire mass of the propellant, SpaceX avoids the thermal spikes that lead to metal fatigue and oxidation. And the injector as a high-speed router. If the pre-burners are the processors and the combustion chamber is the execution environment, then the injector plate is the high-speed router of the Raptor number 3. And in a gas-to-gas system, the injector design changes fundamentally. Instead of complex pintles or swirlers designed to break up liquid sheets into droplets, the Raptor's injector utilizes a series of coaxial elements designed to shear the two gas streams into one another. The goal is to maximize the surface area of the contact point between the methane gas and the oxygen gas. And because both propellants are gases, they can be injected at much higher velocities than liquids without the risk of blowout. This high-velocity injection creates intense turbulence, but it is a controlled turbulence. It ensures that by the time the gases have traveled just a few centimeters from the injector face, they are perfectly mixed and halfway through the combustion process. And this efficiency is what allows the Raptor 3 to maintain a stable flame front. Even as the engine throttles up and down, adjusting the mass flow to steer the Starship during a landing flip, the gas-to-gas mixing remains consistent. Liquids are difficult to throttle because changing the pressure changes the droplet size, which changes the evaporation rate, which changes the engine's tuning. Gases are much more linear. If you want half the thrust, you provide half the gas. The format of the data doesn't change, only the volume. In summary, the seamless engine, the FFSC cycle, as realized in the Raptor 3, represents the transition from a mechanical view of rocketry to a systems view. It treats the propellants not as bulk liquids to be dumped and burned, but as a continuous stream of energy to be refined, transitioned, and precisely deployed. And by eliminating the phase barrier and embracing the gas-to-gas advantage, SpaceX has solved the fundamental conflict of high-pressure rocketry. They have created a system that is simultaneously more powerful and more stable than its predecessors. The full-flow architecture is the ultimate expression of thermodynamic integrity, a system where every molecule is an active participant in the machine's survival and performance. However, this perfection comes with a terrifying trade-off. To achieve gas-to-gas mixing, you must first create those gases. And to create those gases, you must build a machine that can handle the most aggressive chemical environment known to engineering, the high-pressure, high-temperature oxygen environment. And to understand why this perfect cycle remained a theoretical dream for most of the 20th century, we must look at the oxygen-rich side of the equation, a place where metal burns like wood and the margins for error vanish entirely. In section number 4.3, why it is historically hard, the engineering nightmare of oxygen-rich gas.